Good morning, guys. Today we're going to start thermochemistry. This is something that we'll build on later in Chem 2 for Chapter 18. We do have 3 videos for this chapter, so I hope y'all enjoy it. This one's not so math heavy. The other 2 videos have more math. Alright, so it's all about energy. And remember, energy is anything that has the capacity to do work. Work itself is force over a distance, or force times distance. Some of you may remember that from physics. And then heat is that flow of energy caused by that difference in temperature. Okay, so heat and work are 2 different ways that we can exchange energy. So hopefully you remember kinetic energy. That's the energy in motion. Okay, and then thermal energy is the energy that's associated with temperature. It is a type of kinetic energy. Potential energy, on the other hand, is that stored energy, and it's due to either the composition, so what it's made of, or the position of the object. For us, we're going to talk about it being stored in the compound. So we have 2 major types of energy, kinetic and potential, so energy in motion or stored energy, and then they will break into lots and lots of different types of energy. There's tons, but specifically in this unit, we're going to be focusing on that thermal energy. Some other forms of energy, I'm not going to test these, but you just need to know them. Electrical is the flow of electrical charge, so that's a type of kinetic. Thermal, we've already talked about. Light or radiant energy, that's the energy transitions in an atom, so that's also kinetic energy. It's about those electrons moving around normally. Okay, nuclear energy, that's a potential energy. That's the energy stored in the nucleus. And then chemical energy, which we will be talking about some this unit, or this chapter, that's the potential energy that's in between the bonds normally, or just stored in the atom. So the unit of energy, the one we're going to focus on is joules. Okay, that is the one that we use now. It's also the one we're going to use in Chapter 18. An older unit of measure is calories, and y'all are all used to calories on food. And that's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And it is important to note that food calories, which again is what we're used to, has a capital C, and that's 1,000 of the small calories. So a food calorie is the same as a kilocalorie. Here are some energy units and their conversions. I think there is at least 1 homework question on this. All you need is this conversion chart, and it should be pretty easy. Some of you, or lots of you, should also be used to those kilowatt hours. That's what our electricity is measured in for your home. So thermodynamics, which is what this chapter is about, is the study of energy and its conversions. And the first law of thermodynamics is the law of conservation of energy. That is the most important one for this chapter. And that's just saying that energy cannot be created or destroyed. This is the same as the law of conservation of mass, but instead it's for energy. So we are going to talk about systems and the surroundings, but not too much because that's more of a physics thing. The system is the part of the universe being studied. And the surroundings are everything around it. Okay, and when energy flows from the system to the surroundings, it's exothermic. That's normally when you feel something getting warm. It's an exothermic reaction, and that's because the surroundings are heating up. And then the energy flowing from into the system from the surroundings, that's endothermic, and normally you would feel it getting cold. So just remember the law of conservation of mass, energy cannot be created or destroyed. We generally just change it into another type of energy. So here in this first image, we've got a lady, she's pushing the spring down, and then when the spring pops back up, so it's got mechanical potential energy, but when the spring pops back up, the ball is moving, so now we've got that kinetic energy. And the conservation of energy does require that the sum of the energy changes in the system and surroundings be 0 because they should equal back out. So when you add them, it's good. Don't forget that delta, that triangle symbol, means final minus initial. So internal energy, and really y'all, none of this is going to be tested per se until we get farther along in the chapter, and I'll let you know when that is. But internal energy, that's the sum of kinetic and potential energy. And a state function is a function whose result only depends on those initial and final conditions, not the process that it uses. So very commonly we see this mountain example. I kind of like using California and Florida. So it doesn't matter what path you take as long as the beginning and end places are the same. That's what a state function is. So back to my Florida and California example, you can take a plane, you can take a train, you can take a car, but as long as the beginning and end points are the same, it's considered a state function. So it doesn't matter the path you take as long as the beginning and end are the same. Okay, so exothermic, that's when energy is leaving the system, going to the surroundings. Endothermic is when energy is entering the system because it takes energy and leaving the surroundings. So we're pulling that energy from the surroundings into the system. So in summary, when that delta E is negative, that means energy is flowing out. When it's positive, energy is flowing into the system. So this is exo, exit is out, into is endo. And then that internal energy, remember that's just the both of them together. All right, so we've got energy exchanged between the system and the surroundings through heat and work. So we will use Q for heat, lowercase q, and we will use W for work. Okay, so when the system gains thermal energy, work can be done on the system and energy flows into the system, which would be the endothermic. When the system loses energy, work is done by the system and the energy flows out of the system. So that would be exothermic. Sorry, y'all, my coffee maker was just a little loud right there. Okay, so energy is exchanged between the systems and it's either in heat or work being exchanged. So heat is the exchange of thermal energy. Okay, temperature is a measure of the thermal energy. So people often use heat and temperature interchangeably, but they're not. And if we have two objects that are exchanging heat, when they both reach the same temperature, that's when we have thermal equilibrium. And we'll talk about that in the next video more. Okay, so we're not going to use this equation as much. We're going to use the next one more. But remember, Q is heat. C is going to be heat capacity. We're really going to focus on the next one again. And then delta T is change in temperature. For this chapter, we will be using Celsius mostly. Okay, for the next chapter, we'll focus on Kelvin. Okay, and the heat capacity does depend on how much of it there is. So 200 grams of water has twice as much heat as 100 grams of water. Okay, so it is mass dependent, which is that extensive property from chapter 1. This is the equation you're going to need. So I call this the Q equals MCAT equation, because it's mass times specific heat capacity times delta T, but the delta kind of looks like an A. Okay, mass will always be in grams. Specific heat is going to be in joules per gram degree Celsius. You may need to do the units for this on the homework or the test, so make sure you know that. And then again, temperature change is going to be in Celsius, and remember this means final minus initial of the temperature. It'd probably help if I could spell today. The dogs are really distracting. Okay. Okay. And heat will be measured in joules, capital J. So here's a list of specific heat capacities. I would suggest you have this available when you do the homework and when you do the test because they don't always give them to you. Okay, and that specific heat capacity is the amount of energy needed to raise the temperature of 1 gram, 1 degree Celsius. And then the molar heat capacity is the same thing, but instead of grams, it's per mole. All right, so let's do a problem. Let me see if I can get the toy away from the dog. All right, they seem to have calmed down a little bit with the squeaker toy. Oh, not yet. Okay, so we've got a temperature, -8 degrees Celsius, and the temperature of your body is 37 degrees Celsius. It gives us a mass. It also tells us copper. That's how we know which specific heat capacity is. It tells us the compound or the element. So how much heat is absorbed when a penny warms from the temperature. So this is Ti, the initial, and this is Tf. Here's my mass. Let me go back and get copper specific heat. So Cs is 0.385. All right, so I have Q is equal to M, 3.10 grams, times specific heat capacity, 0.385 joules per gram degrees Celsius, times -8 degrees minus 37 degrees. Sorry, that was flipped. It should be 37 degrees because it's final minus initial minus -8 degrees. Okay. Do make sure you either do that subtraction first or you just use the parentheses like I wrote it. I get that Q is equal to 53.7. And remember that unit is joules. Okay, so the Celsius crosses out here, grams crosses out, and all we're left with are the joules. Okay, let's see. Oh, for more practice, 9.2 is good. For practice, 9.2 is similar to the one we just did, except it gives us heat. I do want to do this bottom one though, so it gives us Q is 725 joules. It gives us mass, 55 grams. Aluminum. Initially, okay, so we've got to go back and get aluminum's specific heat, 0.903. So times 0.903 joules per gram degrees Celsius times Tf minus 27.5. Okay, so this one is a little more complicated. So I'm going to get my 55 times my 0.903. So I've got 725 joules is equal to, I'm just going to do numbers for now because keeping up with the units for this is going to be harder. I've got 49.665 TF minus, all I did was multiply the mass times the specific heat capacity, and then I distributed it to TF and 27.5. Okay, so I need to add that 725, so I've got 2090.79 is equal to our 49.665 TF. And I get that TF is 42.1 degrees Celsius. Okay, so it's just a matter of keeping up with what you're solving for, and you should be okay as long as you can do basic algebra. If y'all need help, please let me know. So heat transfer and final temperature. So this is how we often do these kind of specific heat problems. And if you see here, the energy is transferring from the metal to the water. And the only thing that's changing is the sign. And all the sign is indicating is if it's going from the system or out of the system. So this is super important because the heat of the metal is going to be the negative or the opposite heat of the water because they're exchanging that heat between the two. All right, so what is the final temperature of both substances? So remember, we're using Q metal is equal to Q water, but that water is going to be negative. Okay, so my aluminum mass is 32.5 grams. My aluminum specific heat is 0.903. Remember, that's from the chart. And then the initial temperature, so TF, minus 45.8. is equal to negative 105.3 times 4.184, again from the table, and water is at 15.4 degrees initially. Okay, so we're going to do the same thing we just did. We're going to multiply these and then distribute that. Okay, so I've got 32.5 times 0.903. So I get 29.35 TF minus 1344.12 equals negative 440.58 TF minus negative 6784.86. Okay. So once we are to here, we need to get the TFs on the same side and the numbers on the same side. Okay, remember this becomes positive, so 29.35 plus 440. Okay, so I get 469.92 TF is equal to 8,128.97. So then we're going to divide that by the 469. And I get that TF is 17.2, well, let's go with 0.3 degrees Celsius for both of them. So if we look, the aluminum temperature came down to 10. And the mass of the aluminum is way smaller than the mass of the water. The water only went up a little bit. Okay, so make sure at the end that it made sense. Use your number sense. 17.3. If you need more practice, oh, this one is the mass of the block. So we can do this one too. It's going to be the same process, but now we're finding the mass. So we're finding mass of Cu is, okay, the specific heat of copper is 3.85. And the copper's initial temperature was 65.4. and the final temperature was at 24.2. $95.7 grams for the water times 4.184. It's a specific heat. Times 24.2 minus 22.7. Alrighty. And I get that the mass of copper is equal to 37.9 grams. Okay, so all I did was I multiplied all of this and I divided by all of this. Okay, again, let me know if y'all need help. Okay, the last topic, so I do want to stress, this thermal energy transfer and the specific heat capacity equations, those are going to be used as Q equals MCAT, and then Q of metal is equal to negative Q of water. Okay, that will be on the quiz or test and the homework. The rest of it, not as much from this video. All right, so work can also be put in terms, instead of force and distance, it can be terms of pressure and volume, which are things we're going to be using in chemistry. So work is equal to negative pressure times delta V, which is volume. So my negative pressure is negative 1 atmosphere times 1.85 liters minus 1 liter, 0.1 liter. So then I've got negative 1.75 atmospheres times liters. And then it does want us to convert to joules. In 1 atmosphere a liter, it said there's 101.3 joules. And I get negative 177 joules. There it is, negative 177 joules. So these are real simple. There may be one question I don't really remember, but they're not hard if you get them. Okay, let's do one more. Okay, remember for this one, delta E is equal to Q plus W. So Q is 875. Let's go ahead and do W. So W is 1.02 atmospheres times 1.45 liters minus 0.255 liters. I get negative 121.89. But remember, this is atmosphere joules, atmosphere liters. We got to get that to joules. So times 101.3 joules per liter atmosphere. I get negative 12,347. I said the right number and I wrote the wrong one. Joules. And it says that this is emitted. Emitted means it's exo. So this will also be 875, but it's going to be negative. So this is negative 875 joules plus 12,347 joules. I get negative 13,222, but I do need sig figs, so negative 13,200 joules would be my answer for that one. Okay, so please, as always, let me know if y'all have any questions. And Oh, we're not quite done. This is the last slide. Yeah. Okay. So enthalpy. And we're going to focus on enthalpy in the next two videos, so we're not going to stress on it as much here. Okay. But the enthalpy, that's the sum of the internal energy, so that E, and the pressure times the volume. Okay, H is a state function. This is the most important one from this slide, that the delta H is equal to Q if it's at a constant pressure. Okay, that's all I need y'all to know from this slide. So, as always, if you have any questions, let me know, and y'all have a great day.